So, good morning dear students. So, in the last class we have discussed about two iterative methods for solving linear system of equations, namely the Jacobi iteration method and Gauss-Seidel iteration method. There you have seen that Gauss-Seidel iteration method is having little modification over Jacobi's method. Okay? And I also told that Gauss-Seidel iteration method converges first if you have the positive definite and diagonally dominant coefficient matrix. So, now today we will see about the convergence of Gauss-Seidel iteration method. So, in this case or in general convergence means what? For this case you remember here we have the vectors. Okay? So, we start with some guess vector x naught and using the developed procedure that we did yesterday we obtain x 1 fine. Then using x 1 we obtain x 2 like that till we have the accuracy. It depends upon the norm that I wrote in the last class. So, this should actually converge. So, now if I now first I will show you about the algorithm for Gauss-Seidel method. Then I will go to the convergence from here. Actually we will need some matrix we will develop here while doing this algorithm. So, let us have the last problem that we discussed yesterday. So, that was your 10 x 1 minus x 2 plus 2 x 3 is equal to 6 minus x 1 plus 11 x 2 minus x 3 is equal to 22, 2 x 1 minus x 2 plus 10 x 3 is equal to minus 10. So, with this is the problem that we solved yesterday by Jacobi and Gauss-Seidel both methods. Now, to write the algorithm, what we will do first? We will make this diagonal elements of the coefficient matrix as unity, that we can do if it is non-zero. Remember A j j is non-zero, that is the condition, otherwise I cannot do that division. Okay, fine. So, I can make these all unity. What I will do? I will divide this row by the coefficient of this diagonal element. Okay. See, if I divide by 10, so I will get only x 1 here minus 1 by 10 etcetera. Similarly, here also I can make this coefficient of x 2 as 1 unity. Similarly, the coefficient of this x 3 as unity. That means, I will first do a j j as 1 fine. Then what we wrote yesterday, I will have x 1, x 2, x 3. I will write the x 1 elements here, x 2, x 3 constant. Now, as per the Gauss, Seidel or Jacobi, what we are doing, I will take all these terms, two terms in the right hand side. So, what we will get from here? I will not get here x 1, I will get x 2 by 10 fine. I have divided by 10, then 2 x 3 divided by 10 and the constant term is 6 by 10 fine. Next is your x 2 from the second equation, that means I will have plus x 1 divided by 11. Then I will have plus x 3 by 11 and constant term is 22 by 11. Last one I will get x 3 from the last equation. So, I will have minus 2 x 1 divided by 10 plus x 2 by 10, x 3 I will not have minus 10 by 11. Now, you see this. See, in Jacobi method I have all these as naught if I want to find here 1. Okay? If I want to find here 1, so I have all these as 0 or not, because using the guess value I will use that guess value here. Okay, fine. But if I use Gauss-Seidel method, what are the changes? This is your 1, this is your 1 and this is your 1. Understood? So, if I write in general now, so what we have? If I have here I tell this is m plus 1. So, you are seeing these 3 terms will be m plus 1 and the upper one means if I say this is the diagonal, below diagonal you have what? The current values. Understood? Current values. So, if I have here m plus 1, these will all be m plus 1 and the upper means above this diagonal all elements will have with m. Okay? Now, from here actually we will develop the algorithm. See, now any coefficient matrix A I can write as I plus L plus U, where L is the lower triangular matrix, U is the upper triangular matrix, and remember this L lower triangular matrix diagonal element is 0. Similarly, this upper triangular matrix diagonal elements is 0. So, if I write suppose 3 by 3, so what we will have A11, A12, A13, A21, A22, A23, A31, A32, A33. Fine, but I told you before proceeding to this that I will make all AJJ as 1 unity. Fine. So, I will have these diagonal elements, that means will be unity. Fine. So, I will have 1, 1, 1. Fine. Now, this I told that I can write as I plus L plus U. So, this I can write as I as 1 0 0 0 1 0 0 0 1, okay, plus L. L is will be these elements with diagonal element 0 that I told that this L. Okay. So, what I will get 0 0 0 A21 0 0 A31 A32 0. Fine. So, this is your I, this is your L plus in the upper triangular matrix I will take these elements with 0 in the diagonal. Okay. So, I will have 0 A12 A13 0 0 A23 0 0 0. So, this is your U. So, that means the coefficient matrix A, if we change to unity the diagonal elements, I can write in terms of I plus L plus U. And remember those L and U are lower triangular matrix and upper triangular matrix respectively, but you have the diagonal elements as 0, because that will compensate that unit matrix 1 1 1. Okay? Fine. Now, so I have the system as Ax is equal to B. Fine. I have converted this A to I plus L plus U, I plus L plus U, X as B. This if I multiply with Ix, I will have X. Okay. So, this B I can multiply by L with X and U with X and take on the right hand side. So, I will have what? Minus Lx minus Ux. Okay. So, remember this L and U are those, actually these are this is your L corresponding to this problem and this is your U corresponding to this problem. Fine. Now, as per the Gauss-Seidel method, now if I write the superscript xm plus 1 will be is equal to B minus L x minus Ux. Now, this x will be what? M plus 1. As per this we have seen that lower triangular having the same iteration, the same superscripts. Okay. So, I will have here M plus 1 and this x will have M. So, this is our algorithm for your Gauss-Seidel method iteration. okay, Gauss-Seidel iteration method. So, where it is now clear that this L and U I can find here, because when you have large matrix you have to write in compact form, okay, fine. Now, from here I will develop the convergence criteria for Gauss-Seidel iteration method. Now, you see I can write this from here, or from here what I can write, see this is x m plus 1, this is x m plus 1, I can put on the left hand side same x. So, I can write this as I plus L x m plus 1 is equal to b minus u x m. Just I have simplified, I have taken this on the right left hand side. Is it okay? Fine. I have taken this term now to this. Okay. So, this was the actually algorithm. Now, I will do for convergence. So, now I plus L, see the order of these all matrices and vector. So, this matrix will have order, if it is 3 by 3 system we will have 3 by 3 order, this is U also 3 by 3, B is a vector 3 by 1. Okay. If it is n or 10, so similarly it will be 10 by 10, 10 by 10 or 10 by 1. Okay. So, now I will find the inverse of this I plus L and I will multiply from the left. Okay. That means, I will multiply I plus L inverse from the left on this equation. So, what I will get here? It is I plus L inverse, I plus L is I, and that will be your x m plus 1, and from the left. So, I have I plus L inverse B minus I plus L inverse U x m. Fine. Now, if you see the convergence criteria and the formulae etcetera we generated in Newton-Raphson method etcetera, there also what we are having, the relation between the present iteration and the previous iteration. I need that. So, here the relation is what? This is m plus 1th iteration, this is mth iteration, okay, fine, and this handles actually the convergence criteria, and this matrix. So, this will be a matrix minus I plus L inverse U. Okay. So, let us designate this or denote this by C, that is minus I plus L inverse U, and this is called iterative matrix. Iterative matrix. Now, I have the theorem that I was mentioning yesterday, that the convergence will depend upon this. The theorem is the Gauss-Seidel method will converge for every x naught means guess value that you are taking, every x naught if and only if eigenvalues, because it is a matrix, eigenvalues of this matrix C or the iterative matrix, if I take the absolute value of those eigenvalues is less than 1. Okay. What is that theorem? The Gauss-Seidel method, I am writing GS, it is Gauss-Seidel. Gauss-Seidel method converges for every x naught if and only if the absolute values of the eigenvalues of the iterative matrix is less than unity or less than unity. Okay. So, if I find the eigenvalues, although we have not done eigenvalues with respect to your numerical methods, but you know from your previous classes little bit that determinant of a minus lambda equal to 0 there, but those problems are there. So, we will discuss when we will do the eigenvalue problems. Okay. But just this theorem. So, if I have this x naught and I can find this C, because I have the system A x equal to B, from A I have found all these LU and I. So, I can find this matrix. So, if I find the eigenvalues of this matrix, take the absolute value of those. If it is less than 1, then the Gauss Seidel method will converge for that x naught. Fine. We have another sufficient condition for convergency. Sufficient condition for convergency of Gauss Seidel method is norm of C less than 1. This is the condition. So, if I find the C matrix, take the norm of that matrix. I hope you know what is norm of a matrix. Norm of a vector I have already told. So, norm of that matrix, if it is less than 1, then it converges. This is the sufficient condition. So, let us take one example with respect to this, what is happening. Okay. Test of convergency of the Gauss Seidel method. Test whether the GS iteration converges for the given system. The given system is 2x plus y plus z is equal to 4, x plus 2y plus z is equal to 4, x plus y plus 2z is equal to 4. So, this is your system, given system. Okay. Now, I have to test its convergency. That means, first what I have to do? Make the diagonal element as unity. First step is that. So, that means, from here I will have x, I have to divide this row by 2. Diagonal element is 2, means element is coefficient of x. So, x plus half y plus half z is equal to 2. Next equation again 2 is there with y, okay, diagonal element. So, it is half x plus y plus half z is equal to 2. This is again divided by 2, this 2, 2, 2. Okay. So, this is your half x plus half y plus z is equal to 2. Fine. Now, I can write this, I have the coefficient matrix A from here. Okay. So, what I have as the A I have 1 half, 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 1, half, 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 1. So, this I can write in terms of I plus L plus U now, as we did just before this. Okay. I plus L plus U. That means, I can have your L and U. Your iterative matrix is C is equal to minus I plus L inverse U. Okay. So, now I will write this A as I plus L, L is your 0 0 0, half 0 0, half half 0 plus U is your what? U is your 0 half half 0 0 half 0 0 0. So, this is your L, this is your U. Fine. So, now I have this C is equal to minus I plus L inverse U. This means this plus this I plus L. So, you will get 1 1 1 here. Okay. Fine. If I take I plus L, then take its inverse. So, I am writing directly the I plus L inverse. I plus L inverse you will get as 1 0 0 minus half 1 0 minus 1 by 4 minus 1 by 2 1, and then U matrix we have 0 half half 0 0 half 0 0 0. Fine. So, this is your I plus L inverse, this matrix I plus L inverse, and this is U. So, if I multiply, so I will get the matrix as 0 minus of 0 1 by 4 minus 1 by 4 0 1 by 8 3 by 8. So, this is your minus I plus L inverse u iterative matrix. Now, the sufficient condition is norm of this matrix should be less than 1, fine. So, let us find the norm. So, norm of C, I have to find now norm of C. What is norm of C? Norm of a matrix, if Frobenius norm we use, then square root of square of all the elements, square of all the elements summation. Okay. So, I have that means square root of one 2 because it is 3, otherwise it is in general it is n. So, I have to take all the square of that and then square root. So, I have square root of 1 by 4, 1 by 4, 1 by 16, 1 by 16, 1 by 64, 9 by 64. If I do this calculation, I will get 0.884 which is less than 1, fine. So, in this way I can find the sufficient condition. You can find eigenvalues also, okay, fine. So, it is clear. So, given the system, first convert this having the diagonal elements as unity, then find I plus L plus u, L and u, find minus I plus L inverse u and see the norm. So, I have this is Frobenius norm. Similarly, I can use other norms also, column sum, row sum, we have different norms also. So, if you use those norms also, then this number may be different, but it should be less than 1. If in one norm it is less than 1, other norms also it should be less than 1. Okay. So, it is not that you have to use only Frobenius norm, you can use column sum, row sum, other norms for the matrix. Okay, fine. Okay, now, so this was about the Gauss Seidel iteration method, and we already read that Jacobi method. Now, let us come to one important aspect about ill condition and well conditioned systems. So, ill conditioned and well conditioned systems. What do you mean by this? System means I am telling about the Ax equal to b here. This is a system, na, Ax equal to b, fine. So, what do you understand by this ill condition and well condition? So, as you see the words, this is ill and well, meaning you know, ill and well. Ill means not feeling well, okay? Means something, some disease, something is there. Okay? So, similarly, I can have ill condition and well condition for Ax is equal to b. So, the ill condition is defined, means whether that system is ill condition or well condition. If it is ill condition, then in the computation you may have the problem, okay? Fine. So, how you know that this is ill condition or well condition? So, I have said these have been generated, this Ax equal to b, I already told that it has come from some practical problem, fine. Suppose I take resistive network or some population or somewhere from some physical problems I have this Ax equal to b, okay. So, now if you have the so there will be some data, see A elements means some data is there, na? B means some data is there, okay. So, if you have the system with some data, now I change the data little bit, okay. If I change the data little bit and your result is changed enormously, result means x value, understood. I have A, B is coming from data, suppose B you are inputting, okay. So, suppose I change the B, suppose I do not change first, Ax equal to B, A is known, B is known. I can find X by different methods that you have done, LU decomposition or iterative or whatever. Okay. So, I will get X, X is stored. Now, I will change little bit B. So, if your this X value that you are generating or getting or computing, it is changed enormously. That means what the system is? That means system is ill conditioned, it is not well conditioned. That means, if I have the solution from here X, suppose some depending upon the order, there will be elements. So, X we have. Now, I will change this Ax maybe to B plus epsilon, epsilon is very small, very small I am telling you, I am not telling the large value I am changing, maybe 0.001, okay. I am changing all the elements of B or one element of B. So, if it is changing this X plus suppose 1000 epsilon, means this is also vector depending upon the elements. So, suppose it is 1000 epsilon. So, epsilon is 0.001 also, then it will make change or not this enormously this X. That means, that system is ill conditioned. But if I change this and this is again changed by only epsilon amount, okay, little bit change because you have changed the B, then the system is well conditioned. Understood? So, in the next class we will take one example and we will show by a system that I will have a system simple 2 by 2. Okay. I will find a solution of this, then I will change this B by a very small amount maybe epsilon, and you will see that solution is changed enormously. That means, your that system, that 2 by 2 system itself is ill conditioned. Okay. But in case of see by 2 by 2 I can solve and see, but if you are given 1000 by 1000 equations before solving, see after solving you can see that this is ill or well, okay. But before solving, if I can say I can give you the idea little bit that it is well conditioned or ill conditioned. Ill condition means some design you have some problem. See again I told this is from some practical problem. So, from some design or something you are getting Ax equal to B, you have done some mistake. So, your system may be then ill conditioned. So, you have to change somewhere so that you will get the well conditioned system, you can solve that, you can find the X values, current values depending upon your that resistive networks, you are understanding. So, then for that case we have one criteria for system directly by some formula, so that you can know means and have an idea that whether the system given system is ill or well conditions. Okay. So, these two things we will do in the next class. First is we will show by 2 by 2 matrix how it is affecting depending upon B, and if you have in general some system, how to see that your system is well conditioned or ill conditioned. Fine. Okay. Thank you.